All
All right.
right. Good morning, everybody. Welcome to the November 8th working group meeting. Getting closer to the end of the year already, which is a little hard to believe. Um, we'll start off with our new membership. I see that Clifford Buckingham from Estate Greens has joined us on the call this morning. Clifford, if you'd like to take a minute and just sort of introduce yourself and why you joined the group and yeah, what brings you here?
For sure. Hi guys, I'm Clifford. Started a small scale vertical microgreen business a couple years ago, and we are now transitioning into small scale hydroponics. We see the future of vertical farming starting at home, starting with farmers. Rather than completely changing the script, we want to start small, get new growers in, get them educated, learn how they can grow year round. Hopefully, we'll use all the data that we get from our partnerships with small scale technology companies so that we can record and collect how to use these equipments properly and possibly use it to train vision-based robotic systems. So that's why we joined this group today to hopefully make some great connections with some robotic companies, some leaders in the ag technology space, and yeah, share our vision with the rest of you guys. So thank you so much for having me today. I appreciate it.
Absolutely. Happy to have you.
Thank you.
Thanks very much. Um, all right. With that, we'll pass things over into our presentation for today. I'd like to welcome back Dr. Slava Adamchuk, who leads the Precision Agriculture and Sensor System Research Team from McGill University's Department of Bioresource Engineering. So please take it away.
Okay, thank you, Deng, and good morning, everybody. I hope everybody can see my screen. Yes,
We
it's
can.
good. All right, so we'll continue with what we started with a couple of months ago, probably. Just we talked about some of sensor technologies and so on. Today is a little bit more wide discussion in terms of precision agriculture and its connection with agricultural robotics. I'm Slava Damchuk in the Department of Bioresource Engineering, and most of talk that I'm going to do today is related to field crop cultivation. So basically mainstream application of precision agriculture. But to follow up on introduction just done a minute ago, in our department, we do have probably one of the largest research units focusing on controlled environment agriculture, where we're looking at hydroponics. We have a new hire in urban agriculture going to start next summer, and greenhouses and pretty much anything that you can imagine in terms of producing plants and to some extent animal product for food and some of other biomaterials. So today we are going, and one good option for seminar like this is if you have any questions or so, adjourn during emerge during presentation and just put them in chat. I do monitor that, so we can address those questions as they come in. Well, the topic for today is precision agriculture two-level control problem, and so we'll discuss what it is. And two concepts, it's smart tractors and automated decision support, something that we'll discuss as well. So the future of agriculture, apparently robotics is one topic. So we do have in animal production, crop production. So who knows, maybe this is the farmer of the future, or to some extent current. And I don't know if you've seen this. And this is something that's been dreamed on for many years, actually for several generations. I've seen some like movies made in 50s where there's like fictional ideas of agricultural robotics and so on, and something that um, we've seen. And there is some principal component in this phenomena that it's very well seen in this cartoon. So we do have a lot of new technologies. So there is a computer, radio communication, towers, sensors, drones. But at the same time, it's soil, tractor, plant, farmer. So there is this connection of something that we can modify and something that we'll need to uh, continue with. So there is this report. It's one of German companies that put it together and relied on US Bureau of Labor Statistics. So there was some analytical work done maybe 10 years ago or so, looking at which industry would benefit more from automation. And agriculture is actually one of the top areas. So like who we have above it, just accommodation, food service, manufacturers, transportation, and then agriculture. So we are right there. A lot of work that has to be done is repeatable and so on. Of course, there are issues of safety, liability, and so on that still need to be resolved. There is for many countries it's a labor security issue, so that also need to be addressed. But we in that process. Precision agriculture is basically one of management strategies that allow to engagement of um, new technologies to make production more efficient, more productive, better quality, better profitability, and so on. What you see on the screen, it's official definition of precision agriculture by International Society on Precision Agriculture. So I'm pretty sure everybody has seen many different definitions, but this is what the latest version look like. And right away, I'd like to jump into something that precision agriculture cannot offer. It's of course not a magic tool, and we still have some generic production problems that we need to address. We also have to deal with resources that are available. So we also have to deal with the weather that's getting more and more challenging, and especially on occasional basis. And sometimes we have like even here in St. Lawrence Valley, they tell that flooding is coming every so often, but within last 5 years, 6 years, we had 2-3 major events when flooding was a risk to some farm production practices. We cannot make bad machine do a good job. I'm going to talk a lot today about variable rate technology, but there is a joke in our profession that before we do variable rate technology, we need to learn to do fixed rate technology. And that's also a work in progress, and some of machines do better than others. Also, whatever you produce, you need to sell, and there is economical, political events around the world that also affect production systems. So what precision agriculture can help is diagnose production problems and direct over potential solutions, which could be out-of-box solutions. And the reason we are talking about this right now and quite intensively because of some technologies like GNSS based outer guidance This is a system that you see, something that we develop to test how good our guidance system, like does it really perform the way it's specified in the sales brochure when people come to you. So like how close can we control our equipment with respect to plants, with respect to seed, and so on. And those results of two tests that we did over multiple days and so on. So we have test A, test B. Test A, and by the way, the systems that we developed could measure accuracy of guidance with 1 millimeter resolution. So we were able to quantify that performance at a very detailed level. So what we discovered that when we had machine operated and fine-tuned by engineer who was working with a specific auto guidance system, 95% of time we could get with less than 2 centimeter error. So basically 2 centimeter, it's like this. This is what we physically can achieve. So we are talking about farming by plants. So that's technology that's already available. Of course, test B, it's a similar type of tractor with similar type of equipment that we just got from the farm without any fine tuning and so on. So we just put it on the truck, run it for a couple of days with more different speeds, going all the way from very slow, like some of special operation to really spraying level speeds. And we can see that, again, 95% of time, we can be within 5 centimeters. So it's a reality. We did this test over a decade ago, and that's something that we can work with. So there is a variety of operations. Also machine vision, it's been mentioned earlier today, but there is a progress. Technology is relatively inexpensive, and there is a lot of trick like in software and so on, and computers are faster. So we have this capability. The photographs that you see here, it's basically one of the first prototypes that for cultivator guidance systems that we built for some of organic producers here in Montreal area. And the key comment here is that the camera that you see guiding this cultivator, it's a $40 camera. So we really started with low end, and of course it has some disadvantages, but with this technology we were able to increase speed of operation with preserving beans at very early growing stage, even earlier than what you see on this photograph. And the most difficult component here was working with twin row beans, but even that could be achieved through software. And right now there is a variety of products available to help with this type of operation. Of course, if you do overlapping, skipping with your seed placement, with material placement, especially plant protection material placement, there is no excuse, because the technology is out there, and some of the controllers are quite reliable. You can go 20 kilometers per hour, and still, like we are talking about milliseconds in terms of response time. And it could be either sensor driven or preset through shapefile. So something that I'm going to discuss in a minute. And if we're looking at adoption of these different technologies, of course, Purdue University Precision Agriculture Services Dealership Survey, it's one of the most comprehensive materials that's been available since 2000. Looking at a variety of technologies, and we can see like with auto steer, with some of the fleet management and so on. It's technologies that already we are talking about mainstream adoption, because like 2/3 of users already exposed to this, especially if it's customer applicators. So they already there. But there is a catch here, and that's if we're looking at the variable rate technology side. So here we see that some of technologies are less robust, and the rate of adoption is a little bit slower. So a lot of today's discussions were related to that. So how can we get things together? Variable rate technology is important a topic for precision agriculture. So it is obvious that skipping, overlapping, or placing agriculture inputs outside the cropping area should be avoided. So no questions there. And if we can achieve this, we've seen some publications that up to 70% of chemicals can be saved because of this. So this means cleaner environment, less cost of operation, and so on. So that's given. But at the same time, like here in Canada, we are following 4R nutrient stewardship. I would probably add a couple others. So right fertilizer source, right rate, right time, right place, but also under right rotation, right tillage. Because every time we start talking about precision agriculture, we are talking about no-till and improved crop rotation for regenerative agriculture, sustainable agriculture. So those components are also quite important. We do have technology already on the market. This is a photograph 2012. So in experiment, we put together components from different vendors. But this machine on the same path could do variable rate seeding, variable rate application of UN, so liquid nitrogen, and variable rate application of three granular materials, basically potash, phosphorus, and sulfur, and each of them on individual rate, and each of them put on the machine through a slingshot, Canadian technology, now owned by Raven. And agronomist could verify what the quality of application in real time. So again, I'm talking about 12 years ago. Now it's a mainstream technology option with majority of different different system. So, but the maps that we are putting there, so there is a lot of questions of which map should be used to put this. So I just have another snapshot of like slingshot operation. You get those materials in batches and so on. And when we work with some of these pioneers who put this technology in use, they said just understanding like what's went wrong and how much material was actually applied in different parts of the field, like doing an inventory of operations. It's one of major benefit of this technology. So when we look at return of investment on many of the technological innovation, the majority of this is coming from systematic changes, so something that, for example, people still go uniform rate application, but have much better understanding of what that rate is supposed to be, because engaging economics, engaging grid sampling, or some more intensive mapping technique. Like quality control, improved logistics would be the next big impact. With majority of variable rate technology, it's a relatively minor increase. Like you really need to have very specific production system with strong special dependencies that you can address and so on. I'm going to mention a few related items later in this talk. But when I'm talking about economical benefit of variable rate technology, I'm talking about comparison apple to apple, because a lot of studies, you can see that people go with farm no optimization, then going all the way to variable rate technology. Of course, you will have like $100 per hectare benefit and so on. But like if you look closely, a lot of this is just because improvement of the system itself, rather than because of redistribution of the agricultural inputs. So what does impact on profit? It's not just the rate itself. It's a lot of different factors that we need to consider. So it's fertility, water availability, cost of operation, like time, weather, how fluctuation of prices, and of course in terms of management, so rotation, tillage system, input cost, depreciation, and of course application rate. So within this system, we have few variables that we can consider as constraint variables, so like fixed, and one or two variables that we can actually optimize. And that's what brings us to this two-level control, which actually quite important when it comes to automation. It's this concept has been popular in industrial engineering for quite some time, and it seems like this concept is most appropriate for agriculture at this stage. So at the upper level, which is advisory services, that's what define site-specific needs at large. So what type of cultivar in which soil, how weather, economics, risk management. So what's the boundaries within which we are comfortable operating? So what's the minimum, maximum application rate, and so on, like access to the material and so on. It's all of this logistics, which also can be optimized using new technologies. And of course, going to variable rate technology, or more generically site-specific management. And here is those three key points. So those three key points have to be met in order to get variable rate technology sustainable. And you really need to have distinct difference in site-specific needs. So at least two conditions that have different needs, period. You need to have means to recognize this variability. That's something that we are going to discuss today a little bit more detail. And you also need to have equipment, responsive application tools. So in terms of technology availability, we have tools that can deliver that variable rate map. The question is it accessible to a specific producer, to a specific area, and so on. And even if you have tools, and even if you know that you have variable needs, if you don't have means to recognize it properly, my recommendation is not to jump into variable rate technology until you have all three met, because we had quite a few instances where people go into what we call overreacting. So you implement variable rate technology, but you end up with more variability or more problematic conditions than you start with. So it's basically paying double penalty, because you investing in trying to fix the problem. It's like trying to fix car by yourself and then ended up going to the shop and having with more problems that you start with. So I don't know if anybody experienced with similar type of situation. So at the upper level control, we are talking about decision support systems. And this diagram shows the general trend that we see. And numericag.com, it's one of prototypes that our group developed, but there is quite a few other companies working on this. This is where you can appreciate benefits of artificial intelligence, especially if you have a lot of data. Unfortunately, we don't have a lot of data in many cases. So we understand that traditional regression approach or deterministic modeling has some limitations. Convolutional neural network and artificial intelligence has other set of limitations. So one being like you can work with limited data, but it's limited in terms of number of factors that you can consider. When you go into artificial intelligence, it's endless opportunities, but you may not have enough data. So we try to find this middle ground, or like sweet spot of where we could look at simulated scenarios And our numeric simulation is basically Bayesian type of approach, where we just simply looking at the data that's available. We looking at similarities between what's in the database in terms of place, time, and management combination. We can access to online resources such as information about soil, weather, economy, and then can provide user with recommendation. So numeric simulations that I mentioned, it's like you're looking at the production function adapted for specific place management and time, and we're looking at a positive net return of cost of whatever operation, so like use of fertilizers. And the objective function is to maximize dollar per hectare. So basically, we're maximizing profitability of this. So numericag.com still active solution. So there is a form that you can fill in. Like we relying on information such as tillage system, rotation, texture, organic matter of soil, weather, like precipitation and crop heat unit and things like that. And then the system will basically find similar observations from previous history and provide distributions based on this observation. So how report looks like everybody wants to have, okay, what's my recommended value? We can give you that value of what application rate is supposed to be. But the issue is that, like, what if you 10% off? What if you 20% off? Is it going to make drastic difference? Probably not. So we give the distribution of expected net return of cost of fertilization over different application rate. But the most valuable is a graph like this. It's a probability map. So it tells you if you're using, and in this case, it's application rate, but it can be any type of scenario. It could be like with forage production, we were looking at, for example, number of cuts that you do per year, or some of other things that you can change. You can model what would be probability of getting different level of profit if you do scenario A, scenario B, C, and so on. You can run those sort of comparisons. So you can do this not for one location of the field, but for several locations of the field. Like you get your analysis done. If you're interested in observing intra-field variability, identify your good, bad, and ugly within single field. And for each of the boundary conditions, you can run decision support systems that will tell that, well, your most probable economical solution for one condition is this, for another condition is this, and then you can feed it in your controller. So this is an example of report with one set of entry conditions with another set of entry conditions, and we see that probability shifts depending on what those conditions are. At the lower level, as I mentioned, basically site-specific crop management. So, and here the bottleneck is sensors and what type of technology, how we can recognize this. We have a machine that can deliver product, like there is no technological limitation. We can do a farming by plant. So for every plant, we can put different amount of nutrients, plant protection material, and so on, whatever is needed. Now, how to recognize how much is needed? That's actually where we are at this moment. So we need to use sensors, and sensors can be deployed two different ways. And this is really important. So a real-time application, then that's when you don't even need GPS. Sensor talks to your controller and changes rate automatically. So it's what a lot of ag economists call a turnkey solution. So something that farmers like, something that difficult to implement, and then tech support for this product will have to receive all the angry calls from producers because the machine doesn't do what it's supposed to. So there is like in some operations where things are relatively simple, we have that connection, but a lot of times information that you need to use to make the decision is not available on that sensor system. For example, some of you might know, might remember Soil Doctor. It's technologies that have been around for many years, like looking at nitrogen application based on EC measurements. But depending on a variety of factors not connecting to EC, you still, like, your response might still need to be adjusted. Another good example is side-dress nitrogen management based on chlorophyll content that's been around for years, and it's basically you have sensor in front or like on a sprayer or so, and then you feed the controller. But what's important that control function is soil dependent. So you do need to have another layer of information. So integrated approach, when you have some information comes in the form of map and another coming as a sensor, that's basically most versatile tools that can be deployed today. So when it comes to sensors, we do have remote sensing capability. And now with Planet Lab and so on, we have almost a daily acquisition of sensor data, whether without extra premium. So you can go do subscription and then you have daily flow of data. With drones, you have a little bit more control when to fly, where to fly, and normally you have a relatively rapid turnaround. So if previously we were talking about at least several days delay between data acquisition and when you can use it for a field operation, now it's less than 24 hours. So you can really get this data in that stream to do variable rate control. But also we have some of this proximal sensing for both for soil, for plants, and in real time. And actually, some of sensors, they are stationary, so they give you that time perspective in terms of how system changes in dynamics. So you have all of this information together. In terms of sensors, we're still going back to the nature of sensing, so we can look, listen, touch, smell, taste, and we have sensors doing all of this, like on the soil, plants. Same, also we have electromagnetic spectrum, and there is quite a lot of products available to cover this different spectrum. And of course, there is a puzzle that we are working with. And now this puzzle is getting more extended because of some new sensor solutions. Soil mapping is still one of critical components. So robotics helping a lot with getting this job done more persistently, more accurately. Like this is one of semi-automated systems that, and it's kind of hard to see on this photograph, but it was like end of August without 6 weeks of rain. So conditions were very dry. Like a sampler, I wouldn't be able to even stick it 1 inch in the ground. It's nothing. But with this system, we were able to get 30 centimeter fixed cores, like on continuous basis, and do composite samples and so on. So that's one of benefits. And of course, on-the-go sensors that can provide different layers of information. Now we have several systems and service providers that can give multiple maps at the same time. Like with various MSP, you get your topography, pH, your organic matter, texture at the same time. This is something that might be interesting to group. This is one of our tests from last year. It's a smallest version of Z-Tractor. It's an electrical robot done for light field duties, and it's connected with our soil health indicator mapping system. So with this system, like you just basically get it loose in the field, and you get in at the same time mechanical impedance, friction, CO2 concentration within pore space, air permeability, as well as EC temperature, moisture content on the same spot. And you can do it like depending on where you are. It could be pasture, it could be pretty much any type of land coverage. And you got observation in terms of biological activities spread across this field, which is probably one of the best indicators in terms of sustainability of your soil resources. So now this diagram is a little bit overloaded, but this is how our group envision development of thematic maps that can be used for prescription purpose, delineation of management zone if you're in that mindset. So you want to just split the field into different areas, and of course temporal data. So a lot of processes they require monitoring how conditions change. And now we see some people pushing not only moisture but temperature and so on, but also looking at nitrate or some vegetation stage or pH, like a specific location changing over time. It's also important for like hydroponic production and so on, when you have the ability to hold sensors stationary and just material flows through them over time. Data integration is a key here, and not only what you get through precision agriculture tools like sensing data, topography, yield maps, remote sensing imagery. It's also like we got labs because of standardization and so on, and we got to have farmer experience. And the dilemma is still like, where do we go? Best management practice versus variable rate technology. To address this, we recommend to use this type of logical chart. So yield is showing bottom line. So is it changing? Like, do you have a problem? It's a kind of before, like precision agriculture tools, especially like variable rate technology, it's to address a problem, but you need to have it to start with. And kind of good and bad news together is that 90% of cases, we do have this situation. We do have variabilities that consistent from year to year. Now, do you know the reason that variability exists? So you basically take your yield data, you compare with everything else, and then there is a logical explanation why you have a problem in the field. Once you identify the problem, can you get it fixed? So is it drainage? Is it liming? Something that you do just once and then you go to uniform treatment, or it's something that property of your site, and then you got to go with variable or site-specific management operation on the long term. One of our ideas here was like, once you have need for variable rate technology, it's a complex process. Like you got to do prescription maps, you got to get special equipment and so on. But what if we deliver product similar to auto guidance, where all you do is set A/B line? Like, can A/B line approach be used for variable rate technology? And that's where this smart tractor concept came to be. So can we have basically smart tractor with low intelligence equipment? You have a lot of controllers and so on. They are more equipment based rather than vehicle based, but most of vehicles now they have with isobus and so on, and controller in the vehicle is actually quite powerful computer. Most of them have maybe 2 or 3 CU units. So at least one of them have that capability to do this. So can we match tractor operation with local condition according to operator defined rules? So we still have operator on board. So can you make that decision within the framework that you are comfortable with? And we want to rely on internal external sensors. So basically anything that can be plugged in isobus network would be signals that read on board, and you can match your like whatever we can control. We can control PTO, we can control hydraulic flow, we can control travel speed, and so on. So everything that ECU already set to control, we can manage this. So this is the overall framework, including prescription maps. If you in mainstream adoption system and you already have like your service provider giving you maps and so on, you can still feed it in. It's just basically location-based control. It's relatively easy to implement. So we have several different versions. I just have a couple illustrations of how this can be implemented. This is interface that we built for iTech controller. It's basically one that used on John Deere tractors. And it does have this A-B line. And there is some formulas and so on. So it's a proportional controller. You just set your boundaries, so your maximum travel speed, minimum travel speed, and whatever sensor feeds. So we were running RTK elevation into this. And when putting liquid cattle manure, you just slow down on high elevation ground and increase your rate. Simple. And with this technology, we were able to unload more manure in specific fields because we are increasing dose only in the area far away from groundwater, so we prevent leaching. And ironically, it actually would correspond to the residual phosphorus in some of these fields because of like low land would have late emergence, so you don't have as high a removal rate, so you have phosphorus accumulation because of potential soil erosion and leaching, and also because of lower removal rate as compared to higher elevation. So it naturally works progressive. Another example would be like on forage harvester. You just put ultrasonic sensor in front of the harvester, looking at the amount of biomass, and change speed control just to make sure that you operate at the maximum possible speed without plugging your equipment. And we did some benchmark in terms of reaction time and so on. It's a few milliseconds. The system can really operate relatively fast. Another example, just taking a planter, putting a few electrical actuator, and getting a moisture sensor in front of planter. And now, like iScan from Varus and Precision Planting, they have those sensors. We probably had one of the first attempts to do that. And we would just change depths of operation. So the logic here is that if you have wet soil and if you put seed at relatively deep, then in cold climate like Quebec, you would delay your emergence by 1 week, and everybody everybody knows what 1 week delay in crop emergence would do. So basically losing maybe half ton, in some cases maybe 1 ton of grain. So to avoid this, the system would just bring seed closer to the surface if conditions are wet. It's a relatively simple application. Now, what I'm going to do with the rest of time is just to go through some of key field operations and talk about like what's the potential there and what different solutions. So we are talking about integration of different data layers to pursue different type of operations. So when we're talking about seeding rate, it's normally topography, some geophysics, water content, alignment rate, pH, some geophysics, optical reflectance, soil compaction, mechanical impedance, water content, porosity, health, microbial activity, optical reflectance, porosity, mechanical impedance, fertilization rate. So again, ion activity, geophysics, vegetation status, removal rate, topography. So this is what we've seen have worked, and those combination of different data layers that are important. So now going by specific operation, tillage, it's like conservation tillage is still a priority. We want to have sustainable system, and continuous no-till is the holy grail here. how to achieve it and so on, you might need to engage some precision agriculture tool. Of course, control traffic, strip till, and so on, because of auto guidance. It's already there, something that can be used. Also need to be cautioned. We got some reports, the way your traffic pattern and so on, sometimes this control traffic can create like channels for water and to propagate and so on. So it can, like there are some conditions that this system may be challenging to implement. Quite a few farmers, especially in zeros, like decade ago or so, we implemented spot tillage. So that's when we can identify areas that really need to take care and then leave the rest of the field intact. And of course, the high end would be variable depth tillage in response to the depths of a plow pen or hard pen, more generically. And there are several technical solutions, and like in certain geographic areas, you really can save like 40–50% of fuel by moving that direction, but it's not as straightforward technology as one would expect. In terms of seed management, it's a changing rate to account for difference in water ability through the growing season. So there is some modeling and so on involved. Like in Nebraska, we had a clear example of site-specific seed needs. It's dryland corners of center pivot irrigated fields. So you do a drop rate in those corners to stay viable economically. And there is a few other examples would be in that arena. Change placement to optimize emergence, I already mentioned. Change the cultivar hybrid in response to local environment. That's something that also been tested, and we had a few examples like ionophorosis sustainable resistant hybrid, for example, can go into areas where you expect ionophorosis based on secondary parameters. Water management, of course, landscaping and improving surface conditions. That's first objective. And with RTK receivers, we have that capability as like any auto guidance operation, you can log the data and you have high quality topography map that can be used for this. Controlled water table, if possible, in some areas in Quebec, Ontario, that's actually important set of technology. Irrigation scheduling, it's a big thing, doesn't cost a lot, but is important. Also, like using long-term forecast and so on. It's optimization routine to deal, especially if you have water quota and so in some drought areas been important. And of course, variable rate irrigation, especially with different rate across the boom. Technology is there. There is a cost associated with this. Basically, if you want to do individual nozzle control, then the cost of your pivot is almost double. So there should be justification to do that, but as there are cases that it could be still viable type of solution. In terms of line management, it's clear that pH is a defining factor here. And the second point is obvious. No lime should be applied to a neutral or alkaline soil. And also variable rate liming in Midwest and basically Ontario, Quebec would be in that environment. Variable rate liming is one of the top ranked variable rate technology. Some of custom applicators still rely on grid sample, and for many conditions, like for example, this Kansas field, you can have see 1 hectare grids on the right, and it doesn't show alkaline strip along gravel road on the northern part of the field. When if you do more intensive type of mapping, like with MSP, U-series system, or even with manual probes I see here, you can identify those areas and just simply don't apply lime in alkaline or neutral conditions, and that has a very positive economical return. And of course, to address difference in buffering capacity, you need to have additional sensors. But we've done testing of like probably 50 or so different fields, and I would say about like 10% of fields that were this really important issue to address. Majority of fields, you're running in specific range of percent-based saturation, so pH can be a guiding factor for liming decision. In terms of nitrogen, in terms of potassium and phosphorus, band placement has been shown, especially with controlled traffic and so on, quite efficient. A lot of this is related to past management, especially livestock use history, manure use history, historic crop removal, basically looking at yield data. Some sensors are geared toward mapping potassium and phosphorus needs, and we can have long discussion about like which one would be appropriate. Like this one is a mid-infrared sensor that we've been using. You can get numbers, but it's still good to separate extreme conditions. But for example, with phosphorus, even few ppm on low end, few ppm would difference would mean 5-10 kilograms of input of recommended input difference, and there is no field ready sensor that can do separation at that low margin. And of course, micronutrients also quite important, and it's another topic of discussion, how it can be blended together. In terms of nitrogen,
Excuse me. Sorry, I
yes.
apologize. We're getting close to the end of our time here for the meeting.
I have about like 3 slides left. That's pretty much it.
Okay. Yeah, if you can just get through those, then we'll be good.
Yeah, so nitrogen apply when it's needed, and there is also predictive approach, reactive approach, using sensors, using different models. In terms of manure, I already talked about this, environmental risky areas, soil health, nutrient availability, improved logistics is one of key components. And in terms of wheat, this is also machine vision and so on. We do see a lot of good reports on using laser with robotic systems, using mechanical weeders. Again, we different scale of machine vision. At low end, this is one of the weed switch box that we built for one of crop advisors, just driving on quadricycle across the field and dialing in what species of wheat can see, and then we can have a herbicide application map based on that. So this is all that I have for today, and I think in chat we had a couple questions.
I didn't see any come through.
Oh, no, okay, that is just your comments on the timing. All right, so are there any questions or comments?
I have a quick question. I wonder if you guys can hear me.
Yeah, okay. One of questions is related to numericag.com. It's actually www.numericag.com. I can write it in the box.
If anybody with a question would please be able to throw it into the chat, then I can connect you later afterwards in order to hopefully, if that's all right with you, Slava, that I can connect some people via email to answer some questions.
Yeah, that's fine. And somebody wanted to ask a question.
Yeah, if whoever that was, sorry, I missed it. If you could just throw your question into the chat, that would be much appreciated. We just have a couple minutes left here, so we just need to get through a couple of things. Thank you very much for your presentation. We really appreciate you joining us again.
Yeah.
Sorry.
In terms of this numeric act, it need to have www in front.
Perfect. Thank you. Conferences, meetings upcoming. We did add one, the Safer Ag Workshop in December 3rd and 4th in Illinois. For project updates, invitation to join Validity Framework Subcommittee. So what we'd like to do is create a small subcommittee within the working group of individuals who would like to help work on building a validity framework. So essentially a standardization for how do we determine if a technology is valid and viable for use in Ontario. If that is something that anyone is interested in, please throw your hand up in the chat. We'll create a list and then we will add everybody who is interested in that to an email, and we can take it from there. Bridget, I know you had something you wanted to add from our survey.
So I'll push the survey stuff to next week, just out of respect for everyone's time. But I did want to mention that for our meeting next week, we're going to do it a little bit different style. This is in relation to the survey feedback that we got, but we are going to do a little bit more of a roundtable discussion for that week's presentation instead of having one speaker. And we're going to try to, as we move forward the next few months, have one of these per month, where it's a bit more of a roundtable discussion on a specific topic. So next week's topic is going to be on data and data integration. So when you're looking at new robotic solutions, how they integrate with the data that's already on the farm or management systems that are already in the fields, and also how they are translatable to different systems. So that's kind of the topic that we'll be looking at with the group.
Awesome. Thanks for that, Bridget. All right. We do have a new funding opportunity quickly, the Agricultural Workforce Equity and Diversity Initiative. The link is there if you want to check it out. That can provide up to $100,000 in funding. The deadline for application is December 3rd. We have some new articles listed, so please definitely check those out to keep up to date. We are at time for the meeting. So thank you everybody for joining us this week. It was a great turnout. Thank you again to Dr. Adamchuk for his presentation. We really appreciate his time. Everybody have themselves a great weekend, and we will see you next week.
All right, and thank you for attention, everybody. Thank you.
Take care, everyone.